Welcome back to our series on electricity and magnetism. In this episode, we're going to talk about capacitance. Capacitance is the ability of a particular construct of conductors to store energy in the form of the electric field. Now, I know that sounds complicated, but let's look at a simple example, the parallel plate capacitor. Imagine that we have two parallel plates. And that means they're basically the same size and the same shape, and they're held a distance d apart. Of course, they have a surface area. These are not the infinite planes of our Gauss's law days. So their surface area in distance gives them this construct, hence the name of parallel plate capacitor. What we're going to use is a battery in order to pump charged particles against the electric field gradient. In essence, I want to move a set of charges from one plate to the other. So we're going to say this one ends up being positively charged, and this one ends up with an equal amount of negative charge on it, because we're actually going to move the charges from one plate to another. And so the two plates gain the same amount of charge. We'll say this one has Q plus, and this one has Q minus. Well, what we've just done is we've created a capacitor. Of course, there'll be an electric field in between. Remember, electric field lines always run away from positive and towards negative, so the electric field lines will all point like this. Again, we'll have to battle against the idea of the edge effect, which we're going to ignore. We're going to assume that all the electric field will be sandwiched in between the two. And because this has planar symmetry, I know that the electric field will be constant over the entire distance. What we're interested in is looking at what the size of the electric field is, and we'll look at that actually through the voltage, the number of equipotential surfaces between these two plates, as a function of the charge. And here's the contention, and you can back this up with experiment. If we hook up a voltmeter here to measure the potential difference between the two plates, as I pump more charge, the voltage increases proportionally. So we end up with this equation. The equation is that Q becomes proportional to the voltage. Well, if Q is proportional to the voltage, then all I need to do is add in one additional variable, a constant of proportionality. I'm going to add that in on the Q side, on the V side, so that what we end up with is the charge as a function of the voltage. And that function will be CV, so that Q will equal CV. C then is the constant of proportionality that turns this proportion into an equation. That constant of proportionality then is called the capacitance. And it turns out it's only dependent upon the geometry of the structure that creates capacitance. First, though, let's talk about the units of capacitance. If capacitance then is equal to the charge to voltage ratio, and that's a constant ratio, which is why capacitance will be constant, notice that it has units of coulombs divided by volts. And a coulomb per volt is known as a farad. That is the unit for it, and it uses the unit capital F for its unit shorthand. Now, just like a coulomb is a very large unit of charge, a farad is a massive unit of capacitance. And in lab capacitors, you're much more likely to see microfarads, nanofarads, and picofarads as the actual capacity of very small capacitors. Well, one of the first things we want to do then is actually calculate then what is the capacitance of a parallel plate capacitor. We know its physical parameters. It has a gap distance d, and it has a surface area of A on its plates. How much charge should it hold per unit of voltage? Well, to do that, we just go back to the definition of capacitance. If it's Q over V, all I need to do is find some function for the voltage of this construct. And of course, that turns out not to be very hard. Calculating the capacitance of any geometry of capacitor is just a function of this. First, I begin with the definition of capacitance. It's charge per unit volt. And then I find the voltage by actually calculating the negative integral of E dot ds. I should be able to determine the electric field for all of these geometries of capacitors I'm looking at. In this case, it's the electric field for a plate of charge. All I have to do is double it because I have a positive plate here and a negative plate here, and therefore the electric field inside is actually twice what it would be for an isolated flat plate. And of course we know what that is. The electric field for this particular configuration is going to be the charge density sigma divided by E naught. Remember, the electric field from a single plate of charge was sigma over 2 E naught, and a parallel plate capacitor delivers twice the field because it has positive charge on one plate and negative at the other, and the field lines reinforce and build. We're not going to go through the derivation of this particular electric field. I'll leave that to you as an exercise. Well, now all we have to do is integrate over the path we're taking. The voltage from one plate to another should just be the integral over d. So the voltage is actually going to be equal to the negative integral from 0 to d of the electric field, which is sigma over E naught ds. And in this case, we could just call it dx. Of course, that's going to be equal to negative sigma x over E naught. And it will be between 0 and d. So that's going to be sigma d over E naught. Now, the fact that the sign is negative doesn't much matter. We're looking for the magnitude of the voltage. If I had integrated from one plate to another, that would have been parallel to the field. From the second plate back to the first is anti-parallel to the field. They both produce the same dot product. The only difference is the sign. So I'm generally going to use the positive sign to represent the positive voltage change from one plate to another. Now I simply replace that into the definition of capacitance. So for a parallel plate capacitor, C would equal the total charge divided by the voltage, which is sigma d divided by E naught. And then we can go one step further. Remember, sigma is nothing more than the charge per unit area. So I can go ahead and make that replacement now, so I can do some substituting and some simplifying. This will be Q E naught, and then sigma actually becomes Q over A times D. And so the Q's can cancel. The A comes into the numerator. And so for a parallel plate capacitor, it's going to be A E naught divided by D. And this is its capacitance. You'll notice it is no longer a function of either charge, voltage, or field. It's only the geometry of the capacitor that determines its capacitance. If I now load it with charge, it will gain a certain voltage according to this relationship. But the capacitance itself is solely a function of the geometry. Let's see why this one makes perfect sense. First, the size of the plates. If I increase the area, I'm in essence giving more room for more charge at the same level of voltage. In other words, I'm increasing the capacitance. I'm making the capacitor larger so that it can hold more charge at that voltage. That's why A is in the numerator of the capacitance formula, because it's directly proportional to its surface area. However, the gap distance reduces the voltage because it reduces the distance between the plates. And the voltage comes from how far through the field you move. Therefore, the gap distance is inversely proportional to the capacitance, because reducing the gap distance for the same area will reduce the voltage and therefore reduce the capacitance. So there it is. That's the capacitance for a parallel plate capacitor. There are two additional ones that are presented by your text reading. One is deriving the capacitance of a spherical capacitor, and the other one is a cylindrical capacitor. Be familiar with the formulas for both of those and how to rederive them. Fortunately, it's the same process. You begin with the definition of capacitance, and then you integrate the electric field ds using the electric field from a cylindrical and spherical charge distribution. Those are easy to acquire through Gauss's law, and once you integrate them, you will then get the formula for the capacitance of a spherical and cylindrical capacitor. The final thing we want to talk about in relation to capacitance, and that is how individual capacitor elements, in this particular case parallel plate capacitors, interact with each other. So let's imagine a configuration where I have three parallel plate capacitors that are actually attached together and are going to experience a charging regimen. Basically, between the points A and B, I'm going to let charge flow in here and basically charge up all of these capacitors, C1, C2, and C3. What I'm most interested in is there a single capacitor or a single capacitance that represents the same as these three individual elements? Let's see if we can actually find that one capacitance that will do the same job. Well, the first thing we have to realize is once these guys are all charged up, there will be a voltage between A and B that each of these capacitors is responsible for a small portion of. That is, as charge flows in, each one will develop their own voltage, but they'll add up to produce the overall voltage. So there'll be a V1, a V2, and a V3. The one thing that we can hold constant though, and that's the charge. However much charge flows into this left side of capacitor 1 has to be out then on the right side, and of course that's connected to the left side of C2. You'll notice this spot right here where the left side of C2 and the right side of C1 are joined by a wire. In essence, all that can happen here is charge transfers from one capacitor to the other. The same thing's going to happen here. And due to conservation of charge, there'll be no creating or destroying charge in those gaps. So whatever charge flows in on the left side will be pushed off of here and onto here, pushed off of here and onto here, and pushed out of here. But it'll be the same charge on every plate. So there'll only be a single Q here. There'll be plus and minus Qs, but each one will be the same in magnitude. And that's enormously helpful. That's going to help us actually determine our relationship here. Okay, as a result of all the charges being constant, something I can say is this: the overall voltage between A and B, that's just going to be equal to V1 plus V2 plus V3. Well, knowing that over here the voltage will be equal to each charge divided by its own unique capacitance, I can rewrite this. V1 is just going to be the charge, the same charge on all of them, divided by C1. V2 is just going to be the charge, the same charge on all of them, divided by C2. And V3 is just going to be the charge, the same charge on all of them, divided by C3. In other words, what it's really going to be equal to is one single charge times the reciprocal of all three capacitances. If we take this one step further, the VAB equals the charge times this whole thing. And if we look over here, again, the VAB is equal to the charge divided by the capacitance, which means if this is the charge and this is the voltage across the whole thing, this must be what I was looking for, which is the equivalent capacitance, CEQ. The problem is here it appears in the numerator, and I know it's supposed to be in the denominator. That is, VAB would actually be equal to Q divided by CAB, the capacitance of the whole, which means 1 over CAB must be equivalent to what's inside of these parentheses, and that's the end of our derivation. 1 over the equivalent capacitance between this point and this point is equal to 1 over each one of the capacitances summed individually. And I can write a general rule for that too, which is anytime I want a capacitance for a set of capacitors that's lined up like this in series, then that equivalent capacitance will be equal to the summation over I of each one of those individual capacitors summed as reciprocals. So when capacitors are added in series like this, we sum their reciprocals and then we reciprocate that final sum. And that will give me the capacitance of the series of capacitors. In essence, what this does is it produces a new capacitance that's actually smaller than any of these capacitances were originally. If I have a set of stock capacitances and I want a lower capacitance, put them together in series and that will achieve it. Okay, there's a second derivation, and that is for capacitors in parallel. I'm going to leave that up to you to complete prior to your homework. Now that we've looked at the definition of capacitance and we've looked at how to calculate capacitance for a particular physical construction of a capacitor, we're going to transition into capacitors as circuit elements. So we'll start looking at the potential and potential energy within them and then how they operate inside of circuits. So this idea of series and parallel capacitors is soon going to become really important to us.